Ich habe eine Frage.
Ja, gut.
Muss man sich selber anmelden?
Nein. Das ist wie ein Übungsblatt. Genau, also das Mock-Examen ist, zählt nur wie ein Übungsblatt. Das heißt, Sie werden dort, was haben wir denn jetzt, irgendwie 87 Punkte finden, aber das wird dann sozusagen runtergerechnet prozentual auf das Übungsblatt. Das ist wirklich nur, ich halte es für pädagogisch sinnvoller, so ein Mock-Examen jetzt zu stellen, damit man, wenn man halt merkt, oh Gott, ich habe da jetzt irgendwie riesen Lücken oder so, dann hat man halt da wunderbar in die erste Januarwoche noch Zeit, um sich die Sachen anzugucken, anstatt jetzt irgendwie als das letzte Übungsblatt ein Mock-Examen zu machen. Das wäre dann zwar näher dran, aber aus meiner Perspektive haben sie so viele verschiedene Prüfungen dann zu dem Zeitpunkt, dass genau, nicht ganz so früchtetragend ist. Genau. Yeah, so sorry. Because yeah, in German, I answered in German. Yeah, so the mock exam, there's no registration. It's really like a voluntary exercise. It's like doing the exercise sheet instead of during the week. You just do it in 1.5 hours next week, and you can choose to do it in class. I will print out, and then I will collect them. Or you can do it online, and online we'll have there's an extra 50 minutes to upload, obviously, right? You don't have to stress out to have it uploaded by 10. Yeah, because obviously taking pictures takes some time too. But yeah, that's the idea. So it's really, this is not an exam, so this doesn't, it counts like a 13th of your exercise. Like you can also do it online. You can also do it online. You can do it online too. Yeah, because more than half the classes, taking part online, which is fine. Like, because I myself remember as a student taking many more classes than like the schedule would allow, just because classes tend to overlap. And I enjoyed that still, that I was able, somehow got around doing that because I was allowed to learn more than, schedule permitted. And so that's why, like, I'm a big fan of making recordings available and having you choose how you learn best. And if it's, and that said, I really enjoy that you're showing up and I have people to talk to and that you ask questions, and that makes it much nicer on my side rather than like, pure Zoom lecture. That's true. It's really like, here, this is how an exam looks like. And the only disclaimer, it might be that the mock exam might be a tad too long. And if that turns out to be true, because like for the real exam, what I will do is the real exam, the tutors will have to sit and time themselves. So that I know, like, the tutors should take like an hour to finish the exam, so that you have in 1.5 hours, you should be totally good in finishing the exam, just time-wise. And I won't do this for the mock exam, because it's like just an exercise. And because they set it themselves, so it's not like now they have to set the exam, so hopefully they forget the answers, so that I had a real trial. Too few tutors problem. Anyway, yeah. So this is lecture 17. And today we are going to derive the concept of detailed balance. And then look at how to program Metropolis Monte Carlo. So this is the advertised, how I call it, cooking recipe, so that you learn the vocabulary to how to do such a program and what to pay attention to. So derivation of detailed balance. We start with the probability to be in a state by stating that this is, I'm in a state Sn. Sorry, actually, can I turn on the lights? Set at time t, and given that I was in state Sn-1 at Tn-1, so this is the full principal probability of being in a state where the times are ordered with Tn being bigger than Tn-1 and T1. And we'll also remind ourselves of the concept of conditional probabilities. Which says that the probability to be in this state Sn at Tn, given that I was in the state Sn-1, Tn-1, and all these previous states before at the given time steps. And again, the times are ordered. Now, I will make use of an important property that we introduced for our algorithm that we're seeking here for. Remember, we wanted our algorithm to sample our state space, and so it had to be ergodic. That was this like I get everywhere, and it will go in circles. It had to be derived, a Bayes data balance, which we'll going to look at today, and it had to be Markovian. And so Markovian was that it doesn't depend on the history. So if I say a process is Markovian, that means that this conditional probability of being in a state Sn at time Tn, which in principle can depend on all previous states that it was in previously. If it's Markovian, then this conditional probability only really depends on the state it was prior. So really only the current state impacts the future state. So we only have to consider this. There's no memory. Now, with the concept of conditional probabilities, I can write down the probability to be in a state S3 at time T3 and being at state S1 at time T1. This joint probability I can write as sum over all intermediate states S2, S3 at T3, S2 at T2, and S1 T1. So if I sum over all states S2, that gives me then the full probability of being in S3 at T3 and S1 at T1. And now I can subdivide this probability into the conditional probability the product of probabilities, the conditional probability to be in S3 at T3, given that I was in S2, T2, S1, T1, and the probability to be in S2 at T2 with being in S1 at T1. So this is really like a lengthy way of using the rule that the joint probability of A and B is the probability of A conditional B and P of B, right? This you might have seen before. It's just like a lengthy way of writing because we want to take the time steps in the states. Now, this simplifies in our case because we know it's Markovian, right? So this actually only depends on S3, T3, and S2 at T2. And so our sum, let me just give me some more space, then becomes sum over S2 And now I want to play, I want to play the same game with the conditional probability for this probability here as well. So I'm using this formula here for this probability as well. And so I can write this now at S2, at T2 conditional S1, at T1, given the probability to be in S1 at T1. And now what I'm actually doing here is I'm summing over all states S2, right? And so summing over all states S2 with these conditional probabilities actually gives me the conditional probability to be in S3 at T3, conditional S1, T1, and the probability to be in S1 at T1. Where we used this, and so we can write now as, we can rearrange this now to show that ST3 at S1, T1, I can write as sorry, let me rephrase the argument. Okay. So the argument that goes is following. So what we did is we wrote this as a function over the states, and then applied, I wrote this as a conditional probability using this sum once, and another time once to arrive at this equation. And this term probability simplified because we know this is that we assume our process to be Markovian, and so arrive at this equation. But now we can do the same rule for this probability straight ahead as well, right? So we can write this probability obviously also as the probability to be in S1 T1 down here, and the conditional probability to be in S3 given that I was in S1, right? So let me just guide you. So this rule we apply here, we apply here, and we apply here. And so because this needs to be true, we can then read off that this, because this is the same, we can read off that the probability to be in S3, given that I was in S1, is given as the sum of the conditional probabilities down here. And so this equation actually has a name. And that's the Chapman-Kolmogorov equation, where, just to be complete, I should note that these times are ordered. Yes?
Why not sum over all intermediate time T2 and only over all intermediate states S2? Because normally I would expect like the probability, like each event, I call it, is the pair of the state and the time. So wouldn't I expect to also need to sum over all times that are possible in between T3 and T1?
Okay, so what I define is I define the time, I set the time steps.
Okay.
So I set the time, and I just ask what are the different states that it could have at that time.
Okay.
While we're doing this, because in the end, what we're aiming for is having a differential equation, and we're going to set the difference in the times, individual time steps to being incremental so that we can take the continuing limit.
Oh, okay. Okay.
And so for a so-called homogeneous Markov process, sorry, I'm just I can simplify. So we know, let me just write it down. For homogeneous process, sorry, why did I give it the time? Didn't mean to, yeah. For homogeneous Markov process, the probability don't really depend on the explicit choices of the times, but only on the difference in time that elapsed. Because so it's sort of time translational invariant. So being in S2 then really only depends for this homogeneous process of the time difference and being S1 in a normalized time set at 0. And this, we introduced the notation to say this is S2, T2 minus T1, S1. So I'm dropping the 0. And now I want to use this probabilities to write down what is properties for the transition between these different states that are happening in the system, right? Remember, what we want to do is we want to find rules for how we explore our state space going from one state to the other through to the others in our state space and sample them in an efficient manner eventually. And so looking at the transition rate, i.e. the transition per unit time, which I denote with a W. And so here I have the transition probability to go from S1 prime to S, from S prime to S. And I write this as, okay, so the probability to be in S at T plus delta T, this is where it comes in, preparing for the, taking the continuum limit, and being in, sorry, no S, S prime at T. This now depends on if I was in a different state at, so either I'm already in state S at time T, then I will be in state S at time T plus delta T, or I'm in a different state S prime at time T, and I have a certain probability to transition into S. What can also happen is that I, and I have to sum over all possibilities that I can also be in, I'm in state S prime and I go to another state, then I won't, that's reducing my probability to be in a state. So I'm starting from S1, I can transition into S, but I can also transition to somewhere else. Or I start in S, and then I will be in S. And if I don't transition at all, I will be in S at a later time too. Let me just write down the terms and then so I have 1 minus, sorry, this is one too many. Two dishes is fine. So here, the probability to be in S, given that I was in S1, S prime previously, is the probability to transition from S prime to S within this time delta T. And it's equal to the probability to have been in S prime and go to S and be, already S prime being equivalent to S. And so you stay, or you lose by transitioning out to somewhere else. Like you have to sum over all the other probabilities to not be there. And so this now we can rewrite. To write what's the probability to go from, I'm interested in the probability to go from t prime at s prime to s at t plus delta t. And I'm going to write this using the Chapman-Kolmogorov, which you hopefully can still see up there. This one. As so I'm introducing an intermediate state, S double prime at t, and summing over this intermediate state gives me then the probability to go from S single prime, t prime to that. This is just really rephrasing, the Chapman-Kolmogorov that we have here in terms of primes. The 2 prime being the S2 state and the single prime, the S1 state. And now I have here this conditional probability that I've already wrote down in terms of my transition probabilities. So what I'm going to do is I'm going to insert this whole for this probability here to arrive at and so note there's a delta here, delta function. So this sum for the first term already collapses to arrive at 1 minus this sum we still take into account. And now I really have to pay attention to all these stupid primes. Okay, this is double prime. No, this is the 3 prime, sorry. Delta t, and we made use of this, S and the delta acting on, actually takes those away, there we go. Yep, and sorry, I still have to copy down the probability. S, t, and then the second term, we still have this sum. So I believe this form is already, let me guide you through it to read this. So I'm interested in the probability to arrive at S, given that I was at S prime at T prime. Take the conditional probability to transition from an intermediate state S prime prime to this S state, given that I am in this intermediate state and I was at this initial state previously. This is like adding to the probability. Or I'm already where I want to be, that's the one here. Or I lose by transitioning out of the state. That's this term again. And with all these prime notations, we can now aim for the continuum limit by rewriting P as T plus delta T T prime minus P S T at S prime T prime over delta T. And that's then, sorry, I'm moving the first term here front this term is this term. And I use more. And this one here is this one, right? And then we're left with the only other term. Let me do this too. Where is it? So it's this term. That is then the last term that I'm copying down here. Minus. And actually, let me, oops. Okay. And now what I'm going to do is I'm going to take the continuum limit here. So I take delta t to 0. And I use that P of S and T I can write as the sum over, this is again the Chapman-Kolmogorov. Sorry, an intermediate state. And then we arrive at, so taking the limit, I will here get P of S T given at S prime T prime over delta T. And so, which I'm okay, sorry, a few more steps. Okay, so what I'm doing now is I multiply this whole equation with P of S and T prime, such that I can use this, I generate these kind of products, right? And then when I have these products, I can sum over the intermediate steps to arrive at this probability. And so when I here take now the limit, I arrive at something like that. And since I multiply it with P of S of T, and I can sum over this intermediate states, we then make it to a direct derivative of now P of S of T. And here, summing and, oh, sorry, purple I usually do. So this is a very fundamental equation. It's called the master equation. And I bet you would have arrived at this equation if I would just ask you to write down the probabilities of a transition. Because what we have here intuitively, with, given that now that we have this mathematical derivation and we know that we have to assume Markovian for this to work out. That's why this was important to show. But what we see here is the change of probability to be in a state S is given by the probability to be in a different state, but transition to my state S, right? This is a gain term. And in its minus, the probability to be in the state I lose if I already was in the state S, but it transitioned to somewhere else. So it's a loss term. And here, just to note, so the probability is normalized. So the sum over all states S of P of S at t equals 0 by any t is 1. So at any t, that means without, for any arbitrary choice of times, this needs to 1 for all t bigger than 0 as well. And so since this needs to be true, what I can do is I can just take the sum over all states of my master equation as well. Okay, and since now d dt, taking the sum over all states s of p of s and t, just 1, so this will give a 0. So this is 0, and this is equal to summing over s and s, right? I'll just copy. So since this is true, I know that the sum over all states of this term has to be equal to 0. Now we aim for an equilibrium state description of our system. So we know that at infinite times, we should reach equilibrium where our probability distribution is given by the Boltzmann distribution, right? So the aim is to have a canonical distribution with the equilibrium probability of a state being given by 1 over the partition sum e to the minus beta Hamiltonian of my state S, with obviously the partition sum being given by the sum over all states S minus beta. And so in a stationary, for a stationary solution of the Markov, the master equation, I expect that this probability, when it reaches a steady state, so when I'm in equilibrium, really goes to this equilibrium distribution. And so since we exactly want to sample the equilibrium states with our Monte Carlo method, this means that I can insert this distribution in here to look at the steady state, to see that what is true, what needs to be true is that S is now equilibrium sorry, wrong. And this condition is now fulfilled. It's trivially fulfilled if this is equal to 0 already. And that's the detailed balance condition, So this is fulfilled by, and obviously it could be fulfilled by other conditions. So it's sufficient, but not necessary, by WSS. This is the so-called detailed balance condition, which we can simplify in one more way because we actually know what the equilibrium distribution needs to be, right? If particularly if I rearrange to have the two equilibrium distributions probabilities on the right-hand side, the partition function cancels out. And so we can rewrite this as that the ratio of S prime over the transition probability to go from S to S prime prime is given by beta H of S minus H of S. And so this is now concludes the derivation of the unit balance condition that I gave you on Tuesday, by the way. And so it's a condition that you can, when designing a transition probability, you can easily check. So now we saw two different choices of these transition rates to really efficiently sample our state space. One is the metropolis algorithm, one with the Glauber dynamics. I mean, just to show again, for the metropolis, which is the most important and the one that you should have in mind, we choose the probability to go from S prime to S as normalization factor ignore E minus beta energy to be in minus the energy of the prime state, or 1 if E and so then inserting this transition probability satisfies theta balance, and so that needs to be checked. Now I would like to switch gears. Okay, so now we have like the theoretical concept behind Monte Carlo simulations looked at, and now we want to put it into action. So really now we're going to talk about the implementation of Metropolis Monte Carlo and all the caveats that you should think about. Okay, but first of all, let's just have an idea of how you implement it. So the example would be the Ising model, and we start by initialization. So we set up lattice sites I, and we define spins, initial spins Si. We define our Hamiltonian that's acting. We set an internal counter n equal to 1. And we have to choose how long we run, and 0 and max. This is the initialization. And then we iterate. So we iterate by, say, we take a random spin and we flip the spin. And then we assess if we want to accept the spin or not according to our Metropolis algorithm. So what do we need to do? We need to calculate the energy difference. So we calculate E minus beta delta E. And we also generate a random number that's uniformly distributed between 0 and 1. And then we make a choice if we want to accept the spin flip or not. And so the way we do it is, if now W is bigger than R, we accept the spin flip. And if W is smaller than R, we reject the spin flip. And this is exactly then following this probability, right? So if the energy difference is the more like the small, if I reduce the energy of my system by performing such a spin flip that are randomly chosen, then I am with 100% likely to accept the spin flip. And if I gain a little bit of an if I increase the energy of the system by performing the spin flip, there is a certain probability that's proportional to the e to the minus beta of this energy difference that I still accept my spin flip. And then, you know, I can, from this, now calculate all variables of my system A, and store for each step n over n naught. What is this n naught here? So as we're going to discuss, so so you flip a lot of spins, right? This is what you're doing with the Metropolis algorithm, or you don't know, right? But you attempt to flip a lot of spins. But if you just flip or not flip a single spin, it doesn't really tell you that you have an independent new statistical state of your system. And so you have to be careful that your the states that you're sampling to calculate average quantities of your magnetization or what the heck are actually statistically independent. And so for that, you want to not sample every single spin flip that you did, but every n naught. And how to determine this n naught, I will show you. So that's why you only calculate then your average quantity as 1 over the n naught number of n naught states that you sampled. Okay. And then you go back and iterate as long as you want, which is specified by your n max up here. So that's the, yeah.
So why is n not known the number of states sampled? I thought it's just after how many steps we choose to kind of keep a state, and now we divide by.
Yeah. So we'll. Sorry. So I was mixing up two things. So okay. So what you do is you start with initial condition, and then you flip spins. But obviously, your initial choice might not be thermalized, right? You're not at the equilibrium state. So, so this simple setup only actually doesn't have this statistically independence that I talked about. But this is about like that you wait for your system to be thermalized, which you decide to be at n naught. Again, I'm going to show you how you can determine that. So at n naught, it's thermalized, above n naught system thermalized. And so that's why I only start sampling above n naught. But I would actually be more careful and not sample every single point after this, after n naught has been, so correctly speaking, this should be n minus n naught, right? Sorry. Then the total number of steps, right? So you store all steps and then you only take the average after it's thermalized. But even if you do that, you are bound to have statistical errors. So you can either, just do it and take along that you know what your statistical error is because you're just sampling all points, or you reduce the statistical error that you're generating by having independent points that you're sampling. And this is really where all the cooking comes in now. Sorry, I'm just referring to it as cooking, but So typically a class will just teach you, this is the algorithm and this is what you use, right? But then if you sit down, you really have to be careful that, and I believe Monte Carlo is really, really versatile, and you're bound to sort of come across it at one point, that you need to know which kind of things do I need to pay attention to. And so there's quite a bunch. Let me start with boundary conditions. We never cared about boundary conditions when calculating the ISO model, right? We always thought took it as to be infinite, but now it's not, right? Like we have a finite number of points that we put into a system. And so what is actually happening to the spin at the boundary? Like how do I write down the interaction rule for the spin at the boundary? I have to think about that. There's two different choices. One is to have a so-called free boundary condition. So that means that I just admit that the spins at the boundary have fewer neighbors. To interact with. That's it. Or I can choose to have so-called periodic boundary conditions. Where the boundary spins interact with the spins on the other boundary of the system. So say I have a 2D lattice, then I would have these spins interacting with those, and these spins here interacting with those on the other side. Which one is better? You have to check. Both have caveats. That's the thing. So there's no, like, you always have to check. You always have to check in your system. Do I run into problems? How do I check? So caution. You have to check in both cases for so-called finite size effects. So that you're, say, for example, you take the free boundary condition and you have a small sample of 10 by 10. Then you're most likely, it may happen that your overall statistics of a full system is dominated by these spins that are having just three instead of, or even two instead of 4 neighbors. Right? Or you have the periodic boundary conditions and you're generating like these long-range interactions that have like a wavelength that's matching the size of your system, right? Because you have this periodicity built in. Both can happen. And so what you need to, you just need to like check, do I have such effects? This you can do by comparing now, for example, check for even versus odd number of lattice sites per dimension. And look at lattices with increasing number of n. And then you see if the average quantities that you get, you just plot them as a function of n, and they should vary if you make n very small. Obviously, you expect to have finite size effects, but if you make n large enough, they should saturate out. And you have to just check lattices of so, and a standard thing would be to go in potence of 2, right? So say you go from 2 to the 4, 2 to the 5, 2 to the 6, and so on. Whatever your computer makes. Okay, boundary conditions. Run a few checks if your system is fine. Another crucial thing is the choice of the initial condition. I need to have the system thermalized before I need to be in this equilibrated state before I should start, measuring my quantities. And there's two. So what I need to see if I'm already thermalized, and I can also be smart in the choice of my initial condition. Like if I know that I'm at very low temperature, right? I'm probing my system at low temperature, then I'd rather start as an initial condition with already a more ordered network, spin system, right? So that it doesn't take me that long to thermalize. Whereas if I'm at high temperature, I can have, I will go for a very disordered system. So the more I know about the system, I can use to reduce my computational time for it to thermalize. So I need to reach. So I can choose the starting. That would be more ordered state for low temperature, or more random state for high temperature. And then I still have to check, right? And so the way to check is that I run, and ideally the order parameter of my system, I calculate the order parameter of my system, and then I will see when it sort of becomes steady and doesn't change as much anymore. And so that's really when it becomes cooking, because like I would love to give you a formula, right? We would, I don't know, I would aspire to have like, a rule, like this is how long I have to run my system to know that, now I'm allowed to take data. And that's why I guess I refer to this as cooking. There is none. There's no rule. You always have to check. Because obviously it depends on how you choose your initial condition, right? If you already try to be close enough and you're doing better in this system because you know a lot about the system, or you have another system where you have no idea and you're just making an educated guess, you always have to look, and you always have to look when you change the parameters of the system, obviously, when you change the interaction strengths, when you change the temperature, you always have to check. And so as a good rule of thumb, what I typically do is I have the system equilibrate. I take times, sampled for the parameters, and I always multiply by a factor of 2 at least. So I wait at least twice the time just to be on the safe side. And then 2. And we check. So you can start with different initial conditions. There's some randomness of how you generate your initial condition. And even say for like my semi-flexible polymers, I wasn't really able to generate very different conditions. And what I then did is that I just, reran this thermalization a bunch of times and then looked at different, where am I, and always add a factor to see. Where we are, statistical error, and this gives you your equilibration time. And so just as a note, this equilibration time you have to do this again if changing system parameters or temperature. And now, sadly, close to the critical temperature. There's a so-called effect of critical slowing down. And the time to equilibrate sort of goes with the correlation length squared. With the correlation length, squared. I don't know, can just Z, which is Z in this case, it's the coordination number, but it's too for the correlation length. And in principle, also the smaller your N, the smaller your equilibration time, but be aware of finite size effects. So you just have to make an educated choice. Okay. Then we have to care about the data acquisition. And so if you want to read more, this is typically like you find in specific books on Monte Carlo simulations. I think in this case, it's actually really like copy and pasting from my own diploma master thesis at the time. Just because I remember I needed to look this up quite a number of times to have this accurately written down. So when we want to measure the magnetization, and so we want to make sure that we take statistically independent samples when we now explore our state space. And so the way to be aware of how independent or, what's the error bar of my data that I'm taking, we have to look at the statistical error. So we now consider the square of the statistical. Which is defined by 1 over, small n. This I can rearrange by writing as 1 over n squared what I'm aiming here for now is that what you see here is I can I rewrote like how I'm taking the average, and so we here see basically an a squared and a variance term popping out, and we here see correlations coming. And these are 2 different measurements of my order parameter A. And what I'm aiming for now is to have a description of how my my statistical error evolves as once I take more and more data points. So I'm gonna transition from J to J plus M. And then rewrite this as 1 over n of this 1n stays, 1n I put in, and completing the sum here, which gives me the a squared minus a squared, right? The standard statistical error that I would assume for an uncorrelated system. And then the second term is really the contribution I get due to the correlations of the samples that I'm taking. And so this I can rearrange as 2 and rewriting as, so what is the statistical error when I go now from one sample, there we go, from one sample and I look at the next and how does it grow up over time? Like how long do I have to wait between taking samples in the end to have this correlation being small? And so since we went from J, we go from to M to N. Sorry. And J. Sorry, minus. And so the way I'm actually taking my data is that I iterate over time steps. So these are now individual iterations, but let me move to description in terms of times. Which basically means that the time of step n is the increment that I have in the times between individual measurements and the amount of steps I took. So this is really the time interval between successive observations. Which should be bigger than the iteration run. So this, how many times, how long, how many steps do I attempt before I start to measure? And So here we have summations, but I want to go to integrations. And so then we arrive at and so this becomes an integral from 0 to time n. And this is time, the Tm, which is the total time. And I'm gonna take this out. And write this as 1 plus So why is it useful to write it in this form? Well, what we have here is now we know that our statistical error is given by the error if there weren't any correlations, which we would assume just from this like if I had statistically independently drawn samples, this would be my normal statistical error. And then because I have correlations between just flipping, say, 5 spins or attempting to flip 5 spins, this correlation between successive spins, this is all lumped up now in this factor of 1 plus. And so I here actually have a correlation function. And this is very fundamental because now I can actually look at, what is the correlation in my system? How does the correlation now depend on the time difference between my initial point I take the sample and how when I take successive samples? And so I can plot this evolution and then see on which time scales do my correlations decay. And then this time scale on which the correlations decay gives me the input to say, okay, if I want to draw statistically independent samples, I want to wait this correlation time before I take data. So I initialize, I thermalize, I have a summer state, I take my first data set, I store the configuration of my space, and then I wait another time correlation sets before I store another state. And then I store all these states, and then I can calculate my average properties, and I would have the normal statistical error. I can also say, like, I don't have the computational resources to take care of these correlations. Then this equation is also very helpful because I can take into account how big my statistical error is. It's okay to have errors in your measurements. You just need to be aware of how big they are. That's fine, right? But either way, it's very important to know that you have this effect and you have to take care of it, or at least take it into consideration so that your values have error bars. So we here now identify this time correlation function, which I would call phi of A that depends on the time. And that's when I'm taking samples. And you can readily read up that phi at t equals 0, A0 and T0, so these are going to be A squared. So this is actually 1. And as time goes to infinity, this function needs to go to 0. So this correlation function decays over characteristic decay time TA. And so I can actually calculate TA if I were to run this long enough. That's one way to determine TA, which again requires you to have a lot of resources. You can also fit, as I'm going to say, sure. And here we assume that phi t is non-zero, so only for a short, small time window, and if I really go to large times, the correlation really decays to 0. And then with that, if I define this, my statistical error is then one plus 2 TA dot t. And what is more practical is now you may also determine the TA correlation time. I.e. the time to elapse between independent samples by, so you can measure directly dA squared, A squared, and A average squared, and use equation above, right? So what you can do is you can just measure all of these, plot them as and plot them to determine TA, right? Or you can directly measure only this phi A of t, and assume it should decay exponentially, and if you fit an exponential, then you get your timescale. Note that this obviously you should only do after you already thermalized, right? So the equilibration time you have to determine first, and then you can do these measurements. Both only. This is obviously a trade-off, because what you could also do, say, you do this exercise and you realize that your equilibration time is very short, but your correlation time is very long. Then you could also say, okay, it's for me computationally much more efficient to not like wait until I have statistically independent samples. I'm much better at just like reinitializing my system and waiting until it's been equilibrated, and then take independent samples by just having thermalized the system independently. That you can obviously also do. And it's typically a good check also to just work with different initializations and compare the evolution from different initial conditions on the statistical error that you measured here, and having the samples being independent, because that then tells you that you really did well. And so this is really now the cooking recipe of what you should consider. So from last week, like the way you set it up, the balance has to hold, it has to be Markovian, and you have to be ergodic, which just means that you're not allowed to, you eventually have to reach all states in the system. And then when setting up, you should be aware of any finite size effects that you need to check for. You need to determine the equilibration time, and you need to consider when you're taking your data such that it's statistically independent, or you're dragging your error bar along. Either way is fine. But you just, I want you to be aware of this so that you can look it up in case it comes up in your future. And now we can, we can say put it to use. And it's been immensely successful method. So examples of Monte Carlo simulations. The 3D, for example, Ising model, where, for example, we can now really determine the critical temperature. A result from Monte Carlo gives KCJ over KTC 0. This is interesting. Imagine you're the one. Right? Okay. Sorry, this is always, I can't stop it. Like, this is always when I'm like, I count my blessing of why I decided to do biological physics. Because I believe there's lots of fields in physics where you care about these last stitches and you put in a lot of effort to find them. And I must say that I appreciate that effort and that, steadiness and keeping going. But I myself really enjoy being able to find new physical concepts, but that's it. Anyway, here we go, because this was just a Monte Carlo, which might seem like easy in a sense of like, okay, I learned to do programming right well, but this is now being compared to, remember that one? This series expansion. So these are now people who sat down and remember, like, wrote down all these high temperature and low temperature series expansions, enumerating all the graphs, not making mistakes in how many times these graphs can pop up. Yeah, right. And then remember, there was this golden rule, like if you go to order 4, to go to order 5 takes you the same amount of going up to order 4. Yeah, that kind of game. Okay, so, and then, but this is here just to to state the success of finding the critical temperature, and with series expansions, we are within 1, 2, 3, 4, 5, 6, the 6 digits comparison. It works. But it turns actually out that other observables, but like certain critical exponents are much more sensitive to finite size effects. So the critical temperature is something that's like one can be very precise, but other results are not as robust. So this is just to sort of stay within the framework of all these magnetic systems that we looked at. But really, Monte Carlo is versatile too for a lot more complicated systems. So that includes systems like fluids, where we look at an ensemble of particles. And a Monte Carlo move here might be to move a randomly chosen particle, a random distance zero delta in a random direction. And so like the challenge in setting up these Monte Carlo simulations, and where it really now then buys into your creativeness and how to set up a system, is again boiling down to a principle, this ergodicity, right? So how do I actually sample my space? So in the spin system, it seems to be very obvious, like I take a spin and I flip it, or I rotate it if I have a XY or a Heisenberg model, right? But if we look at other systems that we want to probe with Monte Carlo, it becomes much more challenging. What is actually a good move of how I change my system? That's like the spin flip would be the Monte Carlo move. And so like fluids, this still seems straightforward. I just have an ensemble of particles and I just pick one and I move it into a random direction by a random distance. And here comes another cooking ingredient that you have to pay attention to, is because obviously you're going to choose like how far you travel your particle to be random, but within a certain bound. And here it's good to also vary this upper bound of how far you move your particle, and monitor like your acceptance rate. So what you want to do with your move is you want to sample the system. But if you keep moving the particles and the metropolis forbids you to accept that motion, you're not really good in and really thermalizing the system, right? Because you're not moving anywhere. You're just spending time moving. Okay. So you want to make these motions small enough that you're still accepting those moves. But you don't want to have 100% acceptance either, because that would tell you that you're only sort of trying to find the absolute minimal energy, but you're not looking at the thermalized state, right? Because so that would be bad either. So like a rule of thumb is that sort of at least half the trials should be accepted, so that you're computationally efficient, but still in a thermalized state. I used to the 25% is fine too, but right, it shouldn't be too bad. Say half the trials accepted. So I have too few tries. I have a slow equilibration, and also the independence, both timescales are going to get very long, and I have too many trials accepted. I run into the space not sampled efficiently and not really being in the terminal state. So I run into ergodicity. 5 minutes. Okay, just a few more because of my past looking at semi-flexible polymers, which are a very general description of any long, stiff systems that you can think of, like polymers, think of like all these devices where we have polymer gels making up our everyday life, and actually making up ourselves in the same way. We're just a mechanical being built of rods in being the the skeleton of each individual cells that are making up our body. And so here, for example, a description would be that I describe my semi-flexible polymer that is as I could, think of this as a curve. I discretize it in units of equal length, and I describe the state by the string of tangents, unit tangent vectors, ordered, tangents to these polymer segments. And then the discretized elastic energy what is then the product of the two successive tangents along the vein, which again, didn't look too bad. We can map this on an icing model, right? Which is true. Like we can actually do a lot of calculations on semi-flexible polymers. But to stay within the realm of Monte Carlo, so for example, here a Monte Carlo move would be that my new trial configuration is just rotating all chains above a randomly, just rotating a single bond and keeping all the others the same. So this would be rotate a randomly drawn polymer segment by a random or by random angles if I'm in 3D. So that would be theta L, Y L, whatever, constituting the rotation matrix. So for example, what would happen is, say I have this configuration here, and then I pick, this is my bond M, and I just rotate it by a random angle, and then just because this one got rotated, all the other ones, I'm trying to do a good job, get rotated obviously as well, right? And it could be that this is a wonderful, easy move, that it's okay, ergodic because you read about it in the literature. But for example, if you want to have a polymer in confinement, because you want to describe how your DNA is actually folded up in the nucleus, then this is actually a large move because you move the rest of your polymer, and it actually if you have an acceptance that the polymer has to stay within the confinement, your acceptance rate with this moves goes a lot down. So, and then a way out would be to come up with a new way of moving. So another alternative Monte Carlo move would then, for example, be so-called crank shaft move, where you consider a polymer and then you take two random points along the polymer, and you draw a line in between them, and you rotate the whole thing just in between these, and that's a more local move. So here, select two random nodes and rotate by random angle. And then again, you would adjust the parameters of the system to have a good acceptance rate. This is just to sort of illustrate the realm of where really creativeness comes into play when sort of trying to understand systems with Monte Carlo simulation. And that's then also concluding for today. On Tuesday, you have the chance to take a mock exam and test your how well you are doing on the material we covered so far. You can take the exam at home, download, print, whatever, solve, and upload again. The exam is designed for 90 minutes. You will have a grace period of, say, 15 minutes or so for the uploading and for printing out, obviously, as well. This doesn't count a lot, right? This counts like an exercise sheet that you're just forced to take in these 90 minutes. I will be here too and hand out written sheets if you really like this is, you know, to take this in person. Both is perfectly fine. And I will hope to get the tutors to also give you feedback before the break so that you have an idea of how you did. The solutions will be uploaded so that you can self-check, obviously, as well. Yeah, and that's concluding for today. Thank you.